Okay, let's get started, please. Okay, let's get started, please. So, let's remember what we're talking about. We're talking about uniform convergence and why uniform convergence is good, right? So, and the last thing that we showed was basically something that would imply that if you have a uniformly convergent sequence of continuous functions, then they converge to something continuous, right? That's basically the last thing we showed. We showed something even more general than that. It would imply that fact, and the reason we show it in that generality is because we're going to use it we're going to use it as a tool today in a case where we don't have continuity. Okay. Okay. So what we're going to talk about today are the interaction of uniform convergence and integration and differentiation. Okay, so like what can you say about uniformly convergent integrable functions or uniformly convergent differentiable functions? Okay, so before if we're going to talk about integration, I have to give you a crash course in integration because we skipped the chapter. Okay, so let me give you just sort of a quick crash course in Riemann integration. Okay, because we're going to need a couple of facts we need to be able to understand what we're talking about. Okay, so a couple of definitions to start off with. So we're going to start off with a function, a real valued function on a closed and bounded interval. Okay, and we're going to assume that it's bounded. Okay, it's a bounded function, bounded real valued function, and we call a set of points x0, x1, x2 to xn a partition of AB. If x0 is less than x1 is less than x2, if they're increasing points, the first one is A and the last one is B. Okay, so this is called a partition of AB. Okay, all it is that you have your interval AB, right? And then you've got a bunch of points. The first one is A, the last one is B, and you've got a bunch of other points. So x0, x1, x2, x3 through xn. Okay, so that's called a partition. Okay, and you're going to build your integrals on these partitions, as you've probably seen before. Okay. Some notation. We're going to let m sub I denote the supremum of f of x as x ranges over the ith interval. Okay, so you have some function. Okay, you have some function. Here's A, here's B. We're also calling that x0 and xn. And then there's the ith interval, right? Going from x sub I minus 1 to x sub I, right? You've got your function, going on here. And then you let capital M sub I is going to denote the supremum of all the values over that interval. Lowercase m sub I is going to denote the infimum. Same interval. Right? And then, and we're going to let delta xi denote the length the length of the ith interval. Okay, and you've probably seen this sort of thing before. And you probably can guess what I'm going to say next. So there's this thing called the upper sum, denoted UPF. Okay, the upper sum of your function, upper sum of f over the partition P. Okay, so somebody gives you a partition, and there's this partition. You have some function over the set, and we define the upper sum. What am I going to define the upper sum to be? Go ahead, Dylan.
So like big M I times delta x and y.
Exactly. Right. We're going to define this to be the sums of the m sub I times the delta x sub i's, as I ranges from 1 to n. Right. So you take your partition. Right. Let me make my partition a little bit coarser so I don't have to do too much drawing here. Right. So you take your partition. Over each partition, you take the maximum value, right? You take that maximum value and you multiply, right? You take the maximum value and you multiply it by the width of the base, right? So you multiply by the width of the base here. On this one, you take the maximum value, multiply by the width of the base. Here, maximum value, width of the base. Whoops, that's not the maximum value. Maximum value times the width of the base, and the maximum value times the width of the base, right? So the upper sum over this partition would be the sum of these rectangular areas, right? Okay, and then of course the lower sum is defined similarly. With the lower values. Okay. Okay. Everybody okay so far? You've probably seen things similar to this in calculus.
Does the partition have to be finite, like just finite number of points?
Yes. Yes. There's a finite number of points. Okay. How we get to infinity is in the next move. Okay. So the next one we do is we say, okay, let's take take the upper sum over some partition, okay, and then look over all partitions. Look at the upper sums over all partitions, okay. You see that as the partition gets finer, right? Suppose I throw in an extra dot here, right? What's going to happen to the upper sum? What's going to happen to the upper sum? Well, over this interval, I'm going to be taking the supremum over a smaller interval, right? So the supremum will decrease, right? Because I'm taking supremum over a subset, right? So if I throw in another point, if I refine my partition, make it finer, then you see that the supremum actually decreases, right? On the left side here, the supremum is the same. On the right side, actually, my supremum supremum decreases, right? And that gives me a smaller upper sum. Okay. So what I'm going to do is look over, let P ranges over all partitions of AB. Okay. And then I take the infimum of all the upper sums. Okay, right? So basically what we're doing is we're seeing what is the smallest value we can get if we look at all possible partitions, right? That is, basically what's happening is we're allowing the possibility of finer and finer partitions, which would cause the upper sums to decrease more and more, and we're looking for the greatest lower bound of all those values. Okay. Okay. So we call that thing the upper Riemann integral over A and B. Okay. So this thing, the upper Riemann integral over so of f over the interval AB. Okay, and as you might expect, we've similarly redefined the lower integral, right? As the supremum over all partitions of the lower sums over those partitions. Okay? Okay, everybody all right? Yes, still.
This is the question about partition. If so 2D, right, would it just be K cells?
Yeah. Yeah, so you would have, right, in 2 dimensions, then you're going to have, you're going to basically have like products of partitions. Right? You'll have a partition here, you'll have a partition here, and then you'll have, you know, the products of those intervals. Other questions? Okay, so so here's the main definition. So definition number 3: if the upper sum and the lower sum are equal, then we say that f is Riemann integrable. And that its integral is that value. Is that value. Okay. Okay, so this is how we do. This is one way of defining the Riemann integral. This is how we're going to do it. Okay, everybody all right? Okay, so let me give an example. So let's let our function be the characteristic function of the rational numbers. Okay. Okay, and let's say this is on the interval 0, 1. Okay, so our function looks like this, right? It's going to be 1 if x is rational, and it's going to be 0 if x is irrational. Okay? So at every rational number, you get a 1, right? Right? At 1, 1/2, right? 1/3, 2/3, right? You get 1s, you know, the fourths, etc., right? So there's countably many points where this thing takes the value of 1, and there's uncountably many points where the thing takes the value of 0. Okay? So, what's the, if I take any partition, let P be any partition. Let P be any partition. Okay. What's U of F of P? Don't blurt out the answer. Think about it for a minute. Okay, turn to somebody nearby and say, it is this. Okay, would somebody like to tell me the answer? What's the answer? What's the answer?
1.
1, right? The answer is 1, right? Because no matter what partition I take, right? No matter what partition I take, well, the maximum value within that partition is going to be 1, right? For each interval, your capital M is going to be 1, right? And so capital M is always going to be 1 because there's always a rational number inside your interval, right? And so all the values are going to be 1. You multiply by the bases, whatever they are. When you add them together, you're going to get 1, right? So this is always going to be 1, and you see that the upper integral of f is the infimum of those 1s. Well, it's just 1, right? And then what's the lower integral going to be? 0, right? Because for similar reasons, the smallest value is always going to be 0, and so you always get 0, right? Right. So you're always multiplying 0 by the width of the base, but that just gives you a bunch of zeros. Okay. So you see that this is actually a non-example, right? This is a non-example. It's a non-integrable function, non-Riemann integrable function. Right, because the upper integral and the lower Riemann integrals don't agree with each other. Okay. Let me ask you a question. What should the integral be? What do you think the integral ought to be? Just your opinion.
0.
I hear some zeros. Zeros. I hear 1. I saw a 1.
It has like no notion of area, so I feel like it should be like undefined.
Okay, so when you take your next course in measure theory, 137, so-called graduate real analysis, you'll find that the integral of this using the Lebesgue integral is 1. Sorry, 0. Sorry, it's 0. Right. And the reason is that the size of the set, if you think about sizes instead of thinking about doing this partition stuff and then looking at the maximum and minimum values, one thinks in sort of the opposite way. You say, how big is the set where the function attains the value 1? How big is the set where the function attains the value 0? Okay. And the set where the function attains the value 1 is a countable set, right? Countable sets actually have 0 area. Okay, they can be covered with as little material as you desire, right? Because, right, if I have a countable set and I have this much material, right? Suppose I have a countable set, right? And I have this much material, right? I can cover the first one with half of this. I can cover the second one with half of my remaining, and so on and so forth, right? And so I can cover all, this is not the real world. This is the world of mathematics. You can keep on dividing forever, right? So I can cover the whole thing with this much material. But I can also cover the whole thing with this much material, or this much material, or this much material, or this much material, right? So what's the area of a countable set? It's actually 0. Right? So you think, okay, well, in terms of time, what percentage of the time is the function 1? It's 0% of the time, right? 100% of the time, it takes on a value of 0. 0% of the time, it takes on a value of 1. We're thinking about the size of the set. The size of the set where it takes on the value 0 is 1, right? So I should get 0 times 1 plus 1 times 0, and that would give me 0. Okay, so that's just to give you a foreshadowing of the kind of integral that you'll see later on. Okay. Okay. Yeah, regrettably, I've never had the chance to teach that class, but it's a fun one. Okay, observations. Some observations. Okay, let's see. First off, say, recall that f is bounded, right? So the values of f lie between some little m and some big M. Okay, so I'm just going to make sort of a very dumb observation. For any partition, the lower sum is bigger than m times b minus a, right? Little m times the width, right? And the upper sum is less than capital M times the width. Okay, that is obvious. Another fairly obvious observation: if you have two partitions, P and P star, and P star is a refinement of P. Okay, so P star has all the points in P and some more. Okay, this is called P star is a so-called refinement of P. Then what am I going to write here? What's the relation between the upper sums? Keisha? The left one is larger, right? As we said a couple minutes ago, right? You're going to be taking the supremum over a smaller set, over smaller intervals, and so the values are going to get smaller, right? And conversely, when you take the infimum over smaller sets, the value gets bigger. Okay, so simple observations. Okay. Okay, simple observation number 3. No, this is not an observation. This is a definition. Not an observation. Okay, so given P1 and P2 partitions of some interval AB, we denote we call the union the common refinement of P1 and P2. Okay, so this is just, you're just putting the partitions together. You call that thing the common refinement. Okay, so I'm going to just say one more thing about the Riemann integral, and that's this theorem that the lower Riemann integral is always less than or equal to the upper Riemann integral. It requires a little bit of proof. You'd expect this to be true, and let me prove it. It will just take a second. Okay, that the that you always have this relation. Okay, so we're going to do this proof by contradiction. Okay, so suppose that the lower Riemann sum is strictly bigger. Suppose we have a lower Riemann sum that is strictly bigger than the upper Riemann sum. Okay. Right, and remember what these things are, right? This thing is the supremum. This is the lower Riemann sum, which is the supremum of the lower sums, and this guy is the infimum of the upper sums. Okay. Everybody all right? Thank you. Okay, so if this sort of thing happened, right? This thing is the supremum of the lower sums. This thing is the infimum of the upper sums. In that case, we can find a lower sum that is bigger than an upper sum, right? So we can find some P1 here and a P2 here, where the lower sum is strictly bigger than the upper sum, right? Because we can make these guys as close to this thing as possible as we desire, and these guys as close to this as possible as we desire, right? Okay, so in that case, there exists P1 and P2 such that the lower sum of P1 is strictly bigger than the upper sum of P2. Okay. Okay, so now let P star be the common refinement, P1 union P2. Okay, right. We saw what happens. With a refinement, the upper sums get smaller, right? So we have that the upper sum of the refinement is going to be smaller than this thing, right? But the lower sum of the refinement is going to be greater than this thing, right? So we get this sort of relation. Right? And you see that's the problem. Right? Because we would have a refinement where the upper sum is strictly less than the lower sum. Right? That's impossible. Right? You remember how we define the upper and lower sums. Upper sum, you take the sums of the maximums, right? Sums of the supremums times the widths. This thing is sums of the infimums times the widths. There's no way that this is going to be smaller, strictly smaller than that. Right? So that's contradiction.
Wait, is that strictly smaller than less equal to?
It's strictly smaller because of this thing here. Right?
I see.
This is less than or equal to this, which is strictly smaller than that. So that strictly smaller gives us that this is strictly smaller than that. Okay. How are you guys doing? I feel like, am I going too fast? Am I going too fast? Close your eyes for a second. Raise the finger if I'm going too fast. Raise the finger if I'm going too slow. Okay, open your eyes, please. Seems like it's about right. It's about right. For, yeah, seems like it's about right. So why do you all look so lifeless? I was looking at like videos of this class from a few years ago, and apparently so like on YouTube somebody wrote, Professor O says, you should all be cheerful, student. Why? Professor O, because you're alive, we're all alive, and life is amazing. And I'm like, my response was, did I say that? Did I say that in class? And somebody said, yes, you did. It's at this, at 31.20 or something like that.
Oh, no.
Yeah, but yeah, so I guess you guys should be more cheerful. Have more energy. What's that?
I would love to have more energy.
You would love to have more energy. Yeah.
Food coma.
Food coma? Oh, that could be it. Yeah, the 1:30 food coma. Okay, let's get going. Okay, let's go on. So that was your crash introduction to Riemann integration. Now we're going to give a result about uniform convergence and integration. So here's the uniform convergence and integration. Okay, so so here we go. So here's the theorem. You have some function. Let's just say they're into R, so that we just talked about Riemann function, real valued Riemann integral functions. You can talk about complex valued ones. So this will also work for complex valued ones, but let's just say it's in R, since we didn't talk about that. Suppose you have these, you have a bunch of functions, and they're all Riemann integrable. And I always write integrable like this. If f sub n converges uniformly to some f on AB, then in fact f is also Riemann integrable. And the Riemann integral of f is the limit of the Riemann integrals of the f sub n. Okay, so this is one of those commutation results, right? The integral of the limit of the f sub n is the limit of the integrals of the f sub n, right? You can take the limit first and then integrate it, or you can integrate each one and then take the limit, and you're always going to get the same answer. Okay, as long as you have uniform convergence, and you recall that we saw that that doesn't work if you don't. Doesn't necessarily work if you don't. Okay, so the proof is kind of cute. Okay. So we say, well, let epsilon sub n denote the supremum of the difference between fn and f as x ranges over AB. Okay, so E sub n tells you, the worst error is the worst error that fn has, right? How far off f sub n could be from the limit. Okay, right? And we know that these guys are uniformly convergent, and so the E sub n's are going to go to 0. Right, so note that the E sub n's go to 0. Okay. Okay, so also observe, also note that f is trapped between f sub n plus e sub n, and f sub n minus e sub n. Okay. Okay, so here we go. Well, each of these guys is, each of the f sub n is Riemann integrable, right? So let's look at this thing. We have the, let's look at the Riemann integral of this, right? F sub n is Riemann integrable. Certainly a constant is Riemann integrable. So we can talk about the Riemann integral of this function, of this difference here. Right. A difference of Riemann integrable functions is still Riemann integral. Okay. That's the same thing as the lower Riemann integral of this. Okay, right? Because being Riemann integrable means that this and the upper sum are equal to each other, right? Okay. So and that is less than or equal to. So by this fact here, that's going to be less than or equal to the lower integral of f. Okay. Right. We don't know that the integral of f exists, but we do know that the lower Riemann integral of f exists. Okay. Right. These guys, being Riemann integrable, are bounded functions. Don't forget. Right? Because we're only talking about bounded functions when we talk about Riemann integrable functions. Okay. Okay. So okay. Now that, by the fact that we just proved, is less than this, right? The lower sum is smaller than the upper sum. I'm sorry. The lower Riemann integral is smaller than the upper Riemann integral. And by a similar trick, we get that this is less than or equal to this thing here, fn plus e sub n dx. Okay? Okay, everybody all right with that? Anybody have a question? Anybody? Jamie? You good? Great. Great. Okay. So we have this string of inequalities, and we're going to make the observation that if you take this thing and subtract off this thing, then that difference is bigger than this difference, right? If I've got some numbers, right, A, B, and C, and D, A, B, C, and D, right, and they are, increasing, then certainly the difference between D and A is bigger than the difference between C and D, right? D minus A is bigger than C minus B. Okay, so that's what I'm going to do here. So I know that let's see. I get that the bigger guy minus the smaller guy is less than the bigger guy minus the smaller guy, but the bigger guy minus the smaller guy is 2 e sub n dx. Right? Because these things cancel out. Right? And certainly this is bigger than 0. Right? Because the upper sum is bigger than the lower sum. As we showed in the theorem.
It's not strictly bigger than 0.
What?
It's not strictly bigger than 0. It could be equal to 0, right?
Yeah, I'm sorry. When I said bigger, I mean bigger than or equal to.
But did we prove that it's strictly less than, like the difference of the upper and lower?
No, we just showed that it was less than or equal to. Yeah, I hope. Yeah. Yeah, remember we showed that this one could not be strictly larger. I'm sorry. Yeah, that this one could not be strictly larger. In other words, it has to be less than or equal to. Okay? Okay, so that's good, right? So that says that the difference between these guys is trapped between 0 and 0, right? Because when we let n go to infinity, let n go to infinity, we get that that the upper sum and the lower sum must be equal. Okay, and thus F is Riemann integrable. Okay, and further, so from this line here, you see that the Riemann integral of F is trapped between this and this. Right? And so again, when you let n go to infinity, you see that this thing is going to be equal to the limit. Right? This implies that the limit of the epsilons of the integrals as n goes to infinity is the Riemann integral.
So that should be minus.
What?
That should be minus.
Oh, yeah. Thank you. Okay. I love analysis, but I'm not sure I can get that across. I guess I cannot make you love analysis. I can try, but.
Interesting enough, is this the epsilon definition of integrals? Do we have one for integrals? We have one for differentiability of integrals.
Do we have some sort of epsilon definition of integrals?
Yeah, epsilon language.
Yeah, there is something like that. Yeah, but in that case you talk about some sort of limit rather than talking about upper and lower sums. There is some way to do it that way. Okay. Okay. So let's go on. I have to be sure to show you something like completely amazing. Okay, we'll get to something completely amazing in a few minutes. But before we do, we're going to talk about uniform convergence and differentiation. Why people like this stuff, it's kind of hard to explain. I like it. I like it, but I know that a lot of mathematicians don't like analysis, right? It's sort of like, I think I mentioned, some topologists said that we're the cockroach, analysts are the cockroaches, like you try to exterminate them, but you can't get rid of them. Yeah, no, I like this stuff. Again, if you want to see some really sort of pretty stuff where everything works out beautifully, I'd suggest taking a course in complex analysis. It's maybe not super deep, but it's really cool. Yeah. Okay. Yeah, but anyway, I like this. I like all of this stuff. Okay. Okay. So remember that we actually saw there's some example in your book, I think, that shows that uniform convergence doesn't imply even uniform convergence doesn't imply the switching. So it doesn't imply that you can commute limit and differentiation. Okay. So we do have the following theorem. So this is sort of like the best we can do, where this is one step in that direction. Okay. So again, suppose you have some differentiable functions. And again, this works if you think about complex value functions as well. So if the derivatives converge uniformly, okay, so if the derivatives converge uniformly, on AB, and here's a kind of funny one. The functions converge at a single point. Okay. Okay. So if you have convergence, just pointwise convergence at a single point, and you have uniform convergence of the derivatives, that's actually pretty strong. Then, two conclusions. One, the original functions converge uniformly. On AB to some function f, and you can commute differentiation and limit. So that guy is differentiable, and its derivative is the limit of the derivatives of the other guys, of the sequence. Okay. Okay. Okay, so let's do it. So part A, we want to show that the f sub n converge uniformly. Okay. So we're going to use the Cauchy Criterion. Suffice it to show that given any epsilon, there exists a time such that if m and n exceed that time, such that if m and n exceed that time, then fnx minus fmx is smaller than epsilon, right? For all x. Right, that's the Cauchy criterion for uniform convergence. Okay. Okay. So we have convergence at some point. We also have uniform convergence of the derivatives, right? That means we can make the difference of the derivatives as small as we want, right? We can make the difference of the derivatives as small as we want. Okay, so let's think about this. Okay, so let's. I'm thinking, should we do it in the sort of opaque way or the non-opaque way? I'll do it in the non-opaque way. Okay, so hopefully this will be more instructive. Okay, so right here we're trying to get control of this thing, right? We're trying to get control of this thing, and we have these two facts. Okay, so let's think. Right, let's think. We're trying to get control of this thing, right? And we know that the f sub n converge at some point x naught. Okay, so so I'm just going to work. I'm going to work that point in, right? This is going to be less than or equal to. I'll write this as equal to fn minus fm. So let me write this as fn minus fm of x. Okay, just to save time, right? That's this, and I'm going to subtract off fn minus fm x naught and add it back on. right? So I've added in 0, a cleverly chosen 0, right? That's one of our 2 basic tricks. The other is multiplying by a cleverly chosen 1. Okay, so now you know what I'm going to do. Triangle inequality, right? Right? Triangle inequality, right? Okay, so why do I do that? Because I can control the size of this thing, right? This thing I have control over the size, right? Right? What about this thing? This thing is the difference of the difference between 2 points of this thing, right? But I can control that using the mean value theorem, right? This will be controlled, right? If I have a function and I'm looking at its difference, if I have a function I'm looking at its difference, the mean value theorem tells me that, right, that's going to be, the mean value theorem tells me that's going to be equal to the derivative at some point, right? But in terms of size, the mean value theorem tells me that the size of this is controlled by, well, is equal to this and controlled by, say, the supremum of f prime times this, right? And this is just a position and velocity statement, right? The change in position is controlled by the change in time times the maximum velocity, maximum speed, right? Okay, so I know that, well, this thing is going to be controlled by the derivative of this difference. But these guys converge uniformly. So I know that their differences can be made as small as I desire. Okay? So you see what I'm going to do, right? You say, well, look, since Fn prime converges uniformly on AB, we know that there exists some n such that if you're past there, then the size of the difference of the derivatives is smaller than epsilon over 2b minus a. Say. Right? Basically, I can make this thing small. Right? This is the Cauchy Criterion. Right? I can make this thing small for all x. For all x in AB. Right? Should I put the x's in? Okay. Okay. So, right. Further, right? Since f and x naught converges, there exists an n prime such that n and n exceeding n prime implies that fn x naught minus fm x naught is smaller than epsilon over 2. Okay, so we want an n, we wanted a capital N that works. Let capital N be the max of, sorry, let me call this n prime and this n double prime. The max of n prime and n double prime. Okay, right? In that case, then if n and m exceed this thing, we get that this thing, we get fn x minus fm x. Sorry, I'm gonna go over here. we get fnx minus fmx is less than this thing plus this other thing. Right? But this thing is smaller than epsilon over 2 by statement number 2, right? By the second starred statement, right? And then this thing is less than or equal to the derivative at some point at well, no. It's less than or equal to, by the mean value theorem, epsilon over 2 b minus a times b minus a, which is epsilon over 2. Right? And so we get the bound that we wanted. Okay, so, right, so what you see is that that the sequence, sorry, that the original functions are uniformly convergent. Okay, so now we have to do the second part, which is to show that that the limit of the derivatives is actually the derivative of the limit. So I'm gonna erase this thing here. Is that okay? Should I wait a minute? Okay, I said that we were going to get to the cool thing today, but I think we're not going to get to it. So the cool thing I was hoping we would get to today is Weierstrass's continuous nowhere differentiable function. That's pretty cool. So it's a continuous function that's nowhere differentiable, right? And it basically blew everybody's minds in the 19th century. And it has a kind of self-similar structure. It's basically some sort of fractal structure. So, but he thought of it, in the 19th century. The great Weierstrass. Okay. Okay, so part 2. We want to see that, remember what we're trying to show? Our claim is that the derivative of the limit is the limit of the derivatives. Okay, so let me rewrite things, and then you'll see that that things actually become very, very simple. Okay, so let phi of t denote the slope of the secant line for f. Okay, right. This is right. If this is your limit function f, here is x, here is t, right? Then this is the slope of the secant line, right? So phi of t is the slope of the secant line from point x to point t. Okay, and similarly, let phi sub n be the slopes of the secant lines for the f sub n's, for the functions in your sequence that converge to f. So you've got these other guys. We know that they converge uniformly to F. Okay. Okay. Whoops, this should be an F sub n. Okay. So we know that the F sub n's, we just showed that the F sub n's converge uniformly to F, and so we have that. So the F sub n's converge pointwise to phi. I'm sorry, the phi sub n's converge pointwise to phi. Okay. Now, if we can show that the phi sub n's converge uniformly to phi, then we can apply our previous theorem, the one that we used to get continuity. Okay, right? If we can show uniform convergence, we can apply the earlier theorem, right, from the other day, from last class, which told us that the limit as t goes to x of this guy is equal to the limit of these guys as t goes to x and as n goes to infinity. Right, that was, do you remember, this was the theorem that we proved last time, right? And, right, and you see what that would give us, right? This thing here turns into the derivative, right? And then this thing on the right-hand side turns into the limit of the derivatives. Right, which is what we're hoping to show equal. Okay, so we play a similar we play a similar argument as to before. So again, let's think. We're hoping to show uniform convergence of the phi sub n's, right? So we're hoping to show that we can get the phi sub n's, right? We want to show that this thing can be made smaller than epsilon, right? That given any epsilon, there's just a time such that n and m past that time imply that this thing is smaller than epsilon for all t, right? For all t. That's what we're hoping to show. Okay. So let's think, this thing here, well, this thing that we're hoping to control is, by definition, right, fnt minus fnx over t minus x minus fmt minus fmx over t minus x. Right? That's just by definition. Right? And I'm going to rewrite that as fn minus fm of t minus fn minus fm of x over t minus x. Okay, and I want to show that that thing is small. I can make that thing is smaller than epsilon. Right? So somebody's giving me an epsilon. I want to show that I can find an n such past which this thing is smaller than epsilon. Okay. Well, what does this remind you of? Turn to somebody nearby and talk with them, like say, we should use blah, 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 blah. We can control that with something or other.
So the next step. X is anything.
How am I going to control this thing? Somebody tell me. I've got some function at some point minus its other value at some other point over t minus x. What do I know? You have a theorem that tells you that this is going to equal something, right? What is it? The mean value theorem, right? So we just use the mean value theorem. And this is going to be fn minus m prime at some c, right? For some c between t and x. Right? Okay. Now, can I make that thing small? Can I make that thing small?
Yes.
Sure, because uniformly convergent, right? The f sub n, remember our assumption, part of our hypothesis was that these guys converge uniformly. In other words, we can make the differences as small as we desire, right? So since the f sub n converge uniformly, we know that there is an n such that if you're past that n, the difference is smaller than epsilon, right? For all x in our domain, right? So that difference, this thing is smaller than epsilon everywhere, right? So we get this, right? So that's it. So, right? So this thing minus this thing is then smaller than epsilon, right? Because this is just one point. This is one of our x's, and we know that it's smaller than epsilon at every point. Okay, so that does it for us, right? We have uniform convergence of these slope functions, right? And since we have uniform convergence, we can apply the previous theorem and get the result we desire. Okay. Okay. So next time, something cool. Weierstrass's continuous nowhere differentiable function. Okay. See you next time.
So we're going to do it Monday or Wednesday?
I'll make Wednesday. Yeah. Sorry. Wednesday.
Okay.